Hey all you guys, gals, and physics pals, welcome to Quantum High, modern physics for high schoolers. Now let's get talking. Now let's talk about Lorentz equations or Lorentz transformations. They were created to back up the fact that two inertial reference frames do not have events that happen simultaneously, which means there's a shift in the x and in the t, so in position and time, but only in one axis. Y and z stay the same. So for x, we have x prime, the distance in the new moving inertial frame, is equal to x, the original position, minus vt over the square root of 1 minus v squared over c squared, which is also equal to gamma times, in parentheses, x minus vt. And we also have the change in t, where you get t prime is equal to t minus vx over c squared all times gamma, where gamma equals 1 over the square root of 1 minus v squared over c squared. The Lorentz transformation also results in a couple things: time dilation and length contraction. I'm going to start talking about time dilation. We'll get to length contraction later in the video. Time dilation relates two different events that happen at different times and saying that those two different events won't happen at the same time difference in a different inertial reference frame. So saying something gets shot like a little laser beam in one reference frame, if you observe that from a different reference frame, that is going to happen at two different, you're going to see that happen, it shooting and it hitting a target at two different times than if you see it in the initial reference frame. The equation is T naught equals T, big T, over gamma. This comes from plugging into the Lorentz equation using the difference in time rather than just T. It solves out and you just get this big T, which is a T term, which is the difference in time, over gamma equals T naught. And T naught you can solve for using your rest, whatever clock or observer is in rest is T naught. And so because T is divided by gamma, T is always slower, meaning that the moving clock is always slower. That's something you usually hear in regards to time dilation. Saying that T naught is equal to T over gamma gives us that T prime, the big T, is always greater than the proper time, meaning that the moving clock, T prime, always runs slow. It seems as this one is bouncing up and down its proper time, this one shifts this way and has more time, so it runs slow to act in the same amount, same period. To provide clarification for where to measure T naught, it's wherever the position is the same. So wherever the observer stays in the same position to witness the two times instead of moving with, that would be T prime. Another thing that happens with Lorentz equations is something called length contraction. And this comes in measuring distance, length. And so this says that proper length equals gamma times L, the contracted length. And how you measure the proper length is when you can measure the position at any point in time. There's no movement involved. You're at rest, and it's from the observer at rest within the system. But if the observer is moving, then you get the contracted length. It's like when you're moving a camera along, like in a panorama, and you're moving too fast, and it shrinks everything up. Since gamma is always greater than 1, you get that the length, since it's multiplied by the new length, you get the proper length is always longer, which is why it's called length contraction. The final implication of the Lorentz equations is something called velocity addition. And it's saying if you're in a moving reference frame and you shoot a little laser out the front, that velocity is going to be different for different observers in different reference frames. If you're in the frame, you're going to obviously just record using v equals v v naught plus at. But if you're in a different reference frame, that's when it gets a little tricky. And to solve that, there's three different equations you have, whether it's in the x, y, or z direction. If it's in the x direction, let's put it into a scenario. If it's in the x direction, say you're on a train and the train's moving along and you have the station here, that's at rest. Then you're on the train and you start walking. That puts you in motion relative to this train, but the train is also in motion relative to the station. And so if you want to know your speed relative to the station, you have to use this equation. It says that the velocity of the person relative to the station in the x direction is the velocity of the person relative to the train plus the train relative to the station divided by 1 plus the velocity of the person to the train divided by c squared times the velocity of the train to the station. Now for velocity addition in the y and z directions, there's another formula. It's essentially the same for both, you just change the numerator. And it's the velocity in the y direction of the person to the station is equal to the y velocity of the person to the train divided by gamma times 1 plus the velocity of the train to the station divided by c squared times the velocity of the person to the train in the x direction, which is really intriguing that the z and the y are related to the x. So for z, it's just the velocity of the person to the train in the z direction, my bad, divided by that whole big denominator. Now the Lorentz equation have a couple uses, well, more than a couple, but in real life, you can measure the life of muons, which are particles which are the same size as protons, but have the same negative charge as electrons. You can follow their decay through the atmosphere, and it's also applicable to anything moving close to the speed of light. It's how you keep the constancy of the speed of light is using these equations and measure like high velocity spaceships, like going to Mars. You can see how long it would feel for the person on the spaceship. So technically, time travel is real, but not in the way we usually think about it. That's all for the video. Thanks for watching. I hope you learned something, and I give you a quantum bye. Get it?